Thanks for the invitation. Since it's a smaller crowd, I'm happy to be interrupted at any point if you want to ask questions. This is a delicate subject, and it's the first time I'm giving a talk about this, so it can be a little discombobulated. So let me maybe tell you, the main thing that I want to do is so Kevin Costello proposed in 2005 a technology which you start with a Calabi-Yau category or some and a little bit of extra structure related to the generation of the Hodge to the RAM, and out of that you should be able to compute in principle Gromov-Witten invariants. So the reason I say Gromov-Witten invariants is because in principle applying this to the Fukaya category, you should be a Fukaya category for some reason that I don't understand, but probably people here know better than I do, should have a canonical splitting of the Hodge to the RAM, and feed that into this machinery, it should produce classical Gromov-Witten invariants in the good old sense. What happened was that paper, I don't know why, it was very difficult to read, and I think it has only 24 citations on Google Scholar as of a few days ago, and this is pretty surprising to me, but I guess it's because nobody ever managed to do one single calculation with this. So I'm going to try to show you how to do a calculation using that proposed procedure, and I will show you that the answer is what you expect it to be. So the procedure appears to be correct. Now, why do we want something like this? You might ask, why is something like this good? It is good because if you know homological mirror symmetry, and if you knew somehow, this is a big open question, but if you knew that this thing does compute Gromov-Witten invariants for the Fukaya category, that would automatically prove mirror symmetry, classical mirror symmetry, as in equality of some Gromov-Witten invariants from the A side and the B side, because these invariants are categorically defined. So that's one reason. The other reason is because it would allow you to define some invariants that previously require very clumsy definitions. I mean, not clumsy, but not very natural, as in FJRW invariants for matrix when you apply categories of matrix factorizations, or any other thing, higher-genus B-model invariants, for example. All of these should act as the definition of the proper definition of them, not through BCOV, and BCOV you should think of as giving you some nice property that these invariants should have. All right. So let me tell you the example that I will work out, and I will begin by discussing the A-model side, so the classical calculation. Before I begin, let me maybe say that this is joint work with my former student, Junwoo Tu. We hope that maybe in a month we'll have a paper out. Okay, so the classical computation is due to Dike graph. Long time ago, I don't know, early 90s. You start with an elliptic curve, E, and you want to compute, so E is the target, and it's an elliptic curve. And you want to compute the F11 potential associated with this, which is a way to package the Gromov-Witten invariants at genus 1, one marked point. This is the only one we'll be able to compute. So the technology should work in arbitrary genus, and there is no theoretical obstruction, but the computational complexity grows significantly as you go to higher genus. So when you compute the 1-1 genus, 1-1 potential, Gromov-Witten potential function, maybe let me call it A for the A model, the answer that you get is this expression 1/24 plus summation d greater than or equal to 1, summation k divides d, k q to the d. And let me explain where this is coming from. This is saying that if you calculate the number of isogenies with a fixed elliptic curve target, this E, of degree D, there's this number which is a summation of the divisors of D. So this coefficient is the number of isogenies of degree D. And this turns out to be the Gromov-Witten invariant of genus 1. So you can see that you have source curves are elliptic curves as well, are genus 1, with one marked point. What I'm not saying here is you are computing the Gromov-Witten invariant by inserting the cohomology class, which is the Poincaré dual class of a point. This is an H2 of E with coefficients in Q. So I don't know, I assume that many people here are familiar with Gromov-Witten invariants, so I'm not maybe going to explain, but you construct the moduli space M11 bar of E with some beta, which is some multiple of the fundamental class, this D times the fundamental class that determines the degree of the maps. And that moduli space has virtual dimension 1 complex, or it's virtual dimension 2 complex, so you need to integrate the 2 form on it. And this is the 2 form that you get. You start with, you take the any point on E, you take its Poincaré dual class, which is a class in H2, and you pull it back by the evaluation map and then integrate. Everybody good? And this is why you get isogenies as opposed to just random maps where the point, the source point of the marked point on the source could land anywhere on the elliptic curve. This forces it to land at the marked point. Any questions so far? This is what the classical Gromov-Witten invariant calculation would compute. This -1/24 comes from a virtual fundamental class calculation. In the case degree, this corresponds to degree 0. Degree 0, the degree 0, in degree 0, the M11 bar has the wrong dimension. It has dimension 2 instead of having the virtual dimension 1. And so you need to do a virtual fundamental class calculation. Questions? Yeah?
Is it obvious why that's the number of isogenies of degree D?
Why this number is this number? Yeah, it's fairly easy. So what is an isogeny? If you think about the elliptic curve as C mod the lattice, you're trying to find a sublattice of index D. Okay? Now such a sublattice can be obtained by choosing two basis vectors which span it. And you can think of as a matrix with integer coefficients of determinant D. But that is determined up to an SL2Z action, which is the choice of basis. So you're trying to find some kind of canonical form for a matrix with integer coefficients, like a Jordan canonical form for a 2x2 matrix with integer coefficients. And it turns out that you can always reduce it to this form, where L is between 0 and K. Okay? So for every K that divides D, you've got exactly K such matrices. That's why this is a coefficient. Does this make sense? All right. In any case, the important thing is that this expression is a well-known thing for number theorists. It's a modular form, and it is exactly -1/24 capital E2 of Q, where this E2 is the Eisenstein modular form of weight 2. Yeah.
This F11AQ is generating series for this.
For the Gromov-Witten invariants, yes.
Is there some coefficients for the generating series?
What do you mean, some coefficients?
Can you write it as
Yeah, this number is a coefficient of Q to the D.
It's just the Gromov-Witten.
Just the Gromov-Witten invariant. Normally you'd put here the pairing between the symplectic form and the beta. But the symplectic form is the thing that has area 1, and you're taking D times the fundamental class of the manifold. So the pairing is D.
And the constant term, is it something times the Gromov-Witten invariant of Z?
No, this is the Gromov-Witten invariant at D equals to 0, and this is times Q to the 0. So these are the coefficients of higher powers of Q, and this is the degree 0 term. So you, in general, if you knew all your Gromov-Witten invariants, you just write them as summation, the Gromov-Witten invariant times Q to Z power.
So this is the one that isn't quite a modular form, right?
This is not, yes, okay, so, yes, so let me say quasi-modular form. Yeah, this is something I wanted to say. This is not modular. It is invariant under Q goes to Q plus 1. But it's not modular under the other transformations in the modular group. It has some nice, so it's quasi-modular but holomorphic. So let me actually emphasize this because this will come out later.
Is it something like the logarithm of the eta function?
Probably. I don't know my modular forms well enough, but I've seen expressions of that sort. The important thing is that I will come back to this. There's a way to fix this with a little modification to make it modular but no longer holomorphic. Okay. So that's the answer we want to get. Now mirror symmetry tells us what we should get. So what mirror symmetry says is that the mirror map for elliptic curves should be tau goes to Q, which is e to the 2 pi I tau. So what it says to us is that Q that we've put there that seemed up until now to be completely a formal parameter, you should think of it as a coordinate on the moduli space of symplectic forms. And that Q should be identified with its logarithm, maybe divided by 2 pi I, where tau should be the complex modulus parameter. So this parameterizes elliptic curves E tau, which is C mod Z plus Z tau. So if you give me a tau in the upper half plane, then I can produce a specific elliptic curve with that modulus. Of course, this is not well defined. It's only defined up to an SL2Z action on tau. But this should tell you how to identify the complex moduli space on the B model side with the A module with the Kähler parameter on the A side. This is what the map should be. So what this says is that from the derived category of E tau, maybe with plus some more data, some extra data, this stuff that I'm talking about the degeneration of the Hochschild-Rao. But you have a specific elliptic curve. You start with the elliptic curve E tau for a particular value of tau, and some extra degeneration data that we'll have to fix. We should compute another potential F11B of tau, so it depends on tau. And what mirror symmetry predicts is that this should calculate exactly the same thing as that, should be equal to F11A of Q under this identification. So it says if you calculate the potential at some value of tau in the B model, it should give you the same value as the potential. We're lucky here that everything converges. So we can actually compare values. Normally, in classical mirror symmetry, you can only really do perturbative stuff around as a power series expansion. But we should be able to compute this information purely from the derived category and some data. And when we compute it, we should get this number. Minus 1 over 24 V2 of Q. So the goal is to somehow have some machinery into which we feed the derived category of E tau, and we tell it we want to calculate genus 1 marked point, and we should get out this number. So this is the what we want to do. Now, let me give you a little bit of a roadmap for how this procedure works. So this procedure that Costello introduced tells us that there are 4 big steps, which I'll try to go over. So there's one step here, which is compute the string vertex. I will explain what everything is at lambda to the 1. So this string vertex will itself be a power series with coefficients in some chains on some moduli spaces. But the important thing is that if I look at the Euler characteristic of a curve of genus 1 marked point, that has Euler characteristic minus 1. So I care about the coefficient of lambda to the 1. This will be the simplest one. That's why I can compute this fairly easily. Okay, so 1 equals to minus Euler characteristic of surface of genus 1 n equals to 1. Okay, this 1 here, this power. This is a calculation that you can do irrespective of what is your target space that you want to calculate for. So this is some calculation that you can do once and for all. If you're going to compute genus 1 marked point invariance for quintic threefolds, this calculation is exactly the same. You do it once, you don't need to do it a million times. Okay? The second thing is find a Calabi-Yau or cyclic A-infinity algebra equivalent to the derived category of the elliptic curve. So I said I want to feed into this machinery the derived category of the elliptic curve, but that is not something that I can describe in an explicit, easy way. But we know that it is that the derived category of coherent sheaves on E tau can be described as being equivalent to the derived category of modules over a particular A-infinity algebra with cyclic symmetry. So I'm going to replace this data by that data. Okay? Now, once I know that, I also need to find analog of the Poincaré dual class of a point, this class that I was trying to insert. In the B model, I also need to insert something, and I need to understand what's the B model analog of that. That's fairly easy. Plus, it's lift to cyclic homology. So this will be hard. This will be a big chunk of our computation. So this guy lives in Hochschild homology. It will be a Hochschild homology minus 1 of this algebra A tau. Maybe let's call this algebra A tau. So this Poincaré dual class of a point will be an element in the minus 1 Hochschild homology of A tau. We know because of the Hodge to de Rham degeneration that this is a quotient of the first cyclic cohomology of A tau, and we need to pick a lifting, a splitting of that map. And finding one lift is not very hard, but finding the correct one is quite a bit of work. And finally, we take this and feed them into Costello's machinery and then do the final computation. So maybe let me say here that the final computation involves something called Kontsevich-Soibelman insertions in ribbon graphs. And out of this comes this number, F11 beta, F11 B of t. Okay, so this is the roadmap. This is what we need to compute. This part only has something to do with the geometry of moduli spaces of curves. It has nothing to do with the target space. This is just a description of the derived category of the elliptic curve in terms of some finite amount of data. And this is something that is an analog of finding that Poincare dual class of the point. And then the output of this and the output of this will be joined together in some calculation to find an actual number. Any questions? Okay. Now let me begin with the simplest part of this, which is the string vertex. I'm just going to tell you the answer. But first I need to tell you what it actually means. So now part 1 is the string vertex. So the observation that is due to Zwiebach and Sen fundamentally, they are physicists who studied this. They have some papers on what's called background independent theory, which is exactly background independent, refers to the fact that I'm doing it on the moduli space of curves without any reference to a target. The statement is that if I define the space F to be direct sum over all G and N of chains on MGN, mod symmetric group N, possibly disconnected, and add a formal parameter lambda, just to keep track of my Euler characteristic. This is a Batalin-Vilkovsky algebra. So let me maybe go over what's going on here. This MGN disconnected refers to the moduli space of curves of genus G and marked points, no target, just honest things, but I'm allowing disconnected things, possibly, so I'm not just parameterizing connected curves. However, I insist that every connected component must be stable, so it's still finite type. Okay? The symmetric group acts on that moduli space in the obvious way by permuting the labels of the punctures. I take that quotient, and I take singular chains on that. The extra power series in lambda is just there to keep track of my Euler characteristic. We'll forget that for the moment. Now I need to explain what does it mean that it's a BV algebra. I won't have time to explain all the details, but what a BV algebra fundamentally is, it's a commutative algebra graded together with a BV operator, which is the order 2 operator, which satisfies certain properties. Now, let me very quickly say what is a BV algebra structure here. The product is given by disjoint union. If you give me two Riemann surfaces, I can form their disjoint union. That gives me another point in here. The chain's functor is monoidal, so since I had a map from 2 copies to 1 copy, that gives me a product. Is that good? The BV operator is something that is a little bit counterintuitive in the beginning. What it does is it sums over all. You've given me a Riemann surface. You sum over all the ways of picking 2 punctures and then sewing them together. But that is not a well-defined operation. For example, from a 3-punctured sphere, if I take 2 points and I want to sew them together, I'm going to get an elliptic curve. But of course, there's only one sphere, but there's a whole slew of elliptic curves. The twist sew operation allows you to take the 2 punctures, and as long as you fix the radius, it is well defined to say that I'm going to go through all the possible S1 worth of gluings. And that is that defines a well-defined S1 worth of elliptic curves. Okay.
So can I ask, the
Yeah.
curves in your MGN, I mean, are they? You said they're stable, so they're allowed to have nodes. I mean.
No.
No.
No, they're stable in the sense that they have negative. Each component has negative Euler characters.
Oh, okay. And
But they're smooth curves.
What about G?
Are the punctures?
Sorry?
Are the punctures? Are you thinking of the puncture as a point or as a disk embedded into it?
To be perfect, so to be perfectly correct, I need to actually think about it as a small disk with a particular identification of a color around it with that.
Okay.
But then I need to mod out by the S1 action. So it's going to be really a model of MGN with punctures, but to be able to define this twist sewing operation, I need to think of them as little disks. Really.
Would you lose anything if you, instead of taking MGN, you took conformal curves or curves with punctures?
That was the question. I think I'm trying to have curves with puncture, but I don't know how to sew a curve at 2 marked points. I know how to mark a curve
with boundaries or with positive area.
punctures. That's what I want to take, but if I take, I need to also tell you how to identify the boundary with a circle. But once I do that, I get something too big. I have an extra S1 worth of information, so I need to mod out by that. All right.
How do you handle? So I mean, if G is 1 and n equals 0,
That's not in my story.
so
G1 equals n equals to 0 is not here.
Yeah.
so it's just right.
Does not exist. And M02 does not exist.
Right.
Only M03 or higher and G1, M11 and higher. So I cannot tell you what the invariant. I cannot directly, in any way, if I fed into this machinery, I would not know how to feed it to calculate P1s with no marked points into a Calabi-Yau threefold. That's why I'm computing F11 and not F10.
Sure.
Okay.
But
Yes.
you don't really lose anything by that, because you can always stabilize by putting divisors over stuff.
Right. That's true. I could use the divisor axiom to calculate. There's other ways to fix this, but for now, this is what's in Kevin's paper. All right. So now the main theorem that Kevin proves, so Costello, is that there exists a unique up to homotopy solution to the equations d plus delta e to the s equals to 0 and S03 equals to 1/6 times the class of a point. and maybe I should have written S equals to summation SGN lambda to the power 2 minus 2g minus n, summation over all g and n. So this SGN lives in chains of MGN. Mod sigma n disconnected everything. Okay, so let me explain what this says. This says that as long as I insist on this boundary condition, which says that I will look for a solution of a particular differential equation inside this BV algebra. I fix a boundary condition to say what it does in genus 0, 3 marked points. And M03, of course, is a point, so and even if I insist on, if I allow disconnected things there, because I insist each component to be stable, to have a negative Euler characteristic, there is no, it's still a point. And I want it to be 1/6 of a point. This is because of the symmetric group action. That's why the 1/6 comes about. And as soon as I insist on that, all the other coefficients of this S are determined by this differential equation. In this differential equation, D is the chain boundary operator, so I take a chain to its boundary, and delta is that BV operator, which is this is called the quantum master equation for those of you who have seen this, but if not, don't worry about it. Okay? Any questions about this statement? Now, the fact that this solution exists is actually seems like a hard theorem, but it's actually very easy to do. The way you prove it, the way you construct this solution is as follows. You just say, I'm going to try to solve this equation term by term by going genus and then higher and higher. Every time you need to calculate a new one, you will know what its D needs to be from lower degree terms. And it will turn out that it lives in a homology group of MGN, which is 0. So saying to solve the equation D of x equals to something in that homology group, it's enough to show that that something is itself closed. Mm-hmm. So you know that there is a solution. The solution is not unique, of course, but Kevin proves that up to homotopy it is unique.
Did Zwieback and Sen
Sorry?
Did Zwieback and Sen do something along these lines?
Oh, sorry, I can't read that. What they did was this. Maybe let me say where Zwieback and Sen came from. What they said is, we would like to get a compact approximation. The problem is that MGN is not compact. And we'd like to get a compact approximation to MGN without compactifying. So instead, to compactify means to add more points to make it compact. What Zwieback and Sen wanted to do was, we'd like to get a large compact set sitting inside MGN on which to integrate. Because we want to think of it as a chain, and we want to integrate on it. Now, what they said was, fix an epsilon that's small, and look at all the curves of genus G and N punctures, which in the hyperbolic metric of constant negative curvature -1 have no geodesic of lengths less than epsilon. So you're thinking about, for example, if you're thinking about elliptic curves, you're thinking about all the elliptic curves that are not too close to the cusp. When you get to the cusp, one of the geodesic gets very small. You're thinking about everything that's not close to the cusp. And then they notice that the solutions, if you put all of them together, they satisfy this quantum master equation. And that's actually a very easy thing to see. You think about what the boundary of this compact set is. It's those which have exactly one geodesic of length epsilon. Then you cut along it. There are two things that can happen. Either two disconnected things show up with no geodesic less than epsilon, or you get one thing of genus 1 less, which has been obtained by a twist sawing. Does it make sense? This is how they thought about it. All right. Now let me tell you, the good thing about this whole thing is that in there are ribbon graphs provide a way to calculate chains on moduli spaces, and I will tell you exactly the solution. So the coefficient of lambda to the 1 in S is given by the following combination of ribbon graphs: 1/2 of this plus 1/4 of this plus 1/24 times this with a T inverse here. Okay, so now this is totally, I've just thrown this at you with no kind of advance warning. But let me maybe try to say what this roughly means. So maybe let me say, after turning an output into an input, so there are some technical issues with ribbon graphs.
So what's going on with the first graph? Is that those loops on the ends?
Those two are white vertices.
Oh, okay,
So-
okay. All right.
Now I've just thrown everything out.
Okay.
Okay. So you need to read Kontsevich-Soibelman. Kontsevich and Soibelman notes on A-infinity algebras and categories tell you that you should be studying ribbon graphs of a particular type. They must have, inside each face of the ribbon graph, inside each boundary component, they need to have a distinguished kind of half edge. So this graph has got only one face, and this is its distinguished half edge, this one with this X here. This ribbon graph is genus 1 and only one face also. And this is its distinguished leg. One here also for the unique face of this one. But those ribbon graphs are also allowed to have output vertices. So you think about them as giving you maps from input faces to output faces, not just inputs. So think of the ordinary faces of ribbon graphs as inputs and those white vertices as outputs. So this lives in M03. It's a chain of degree 0 in M03. This is a chain of degree 2 in M11. And this is a chain of degree 0 in M11, but with this T inverse. So altogether has degree 2. This T is what some people might call U, is the cyclic homology variable, the variable that you put when you rotate, the degree 2 variable. So these two ribbon graphs have one input and 0 outputs. Maybe let me put the number of inputs and outputs separately. Those have one input and 0 outputs. This one has got one input and 2 outputs. Yes?
Where is T in the definition of S above?
Okay. The problem is there was no T, but the way I should have done it, an equivalent way I could have done it, is I could have made the moduli space upstairs to be S1, the marked chain, the marked moduli spaces, where each boundary component has got a marking on it. And then I could have modded out by the S1 action. So when I mod out by I would want to mod out by an S1 to the N action, but because I've symmetrized by sigma n, I really have only one variable left for all the S1s. And so now I have, that thing is actually a module over over C double bracket over the cohomology of the equivariant cohomology of a circle, not. Okay. So it's the usual thing that if you take a space and cross it with S1 and take the equivariant S1 cohomology, you're going to get the cohomology of that thing cross the polynomial ring in T, or Laurent polynomials in T. Okay. Now maybe let me explain just very kind of hand wavy why those coefficients are here. They will always be rational numbers. This 1/2 is a direct consequence of, okay, so there is an issue here. Upstairs, all my punctures are treated equally. So I have n punctures, but they've been symmetrized by the symmetric group action, so they're all treated equally. On the other hand, I need to be able to glue any two punctures. The problem with ribbon graphs is that gluing ribbon graphs along faces does not work well. The way Kontsevich and Soibelman set all of this thing up is that white vertices output vertices can be glued to anything, but input vertices you don't need to glue them among themselves. Now the problem is that that thing you should think of as living in the moduli space of things with 0 inputs and n outputs. If you had n outputs, outputs can be glued to outputs, so I can define the delta operator. And I can also symmetrize them. The main problem is that ribbon graphs can never have 0 inputs, because every ribbon graph will have at least one face, one boundary component. So Kevin introduces this operator which sums over all the ways of taking an output and turning it into an input. That's an isomorphism of moduli spaces. So what is this 1/2? Well, S03 was 1/6 times the class of a point, but that was thought of as living with 3 outputs. If I want to look at all the ways in which I can turn one of the outputs into an input, I get 3 such choices of the 3 points. That makes this coefficient 1/2. This corresponds to S03, but instead of having S03 as having 0 inputs and 3 outputs, which I don't know how to represent as a ribbon graph, I represent it as this guy, which is what I get out of that by turning one input into an output. You'll notice that all of these have one input and some number of outputs. This is what I get by going from all outputs to one input and all but one output. This is a 1/2 here. And then these two coefficients are completely determined by the quantum master equation up here. If you understand carefully how D and delta operate. So the delta, there's only one place where I can do delta, and that is here. So if I do that, maybe let me show this. Delta of this guy 1/2 of this guy is 1/2 times. So I think about these now are boundary components that can be sewed together, and I get 1/2 times this guy with this. So imagine that I've taken those two little loops and sewed them together. This edge becomes this edge that goes around, and in the middle it had a little tack. And these two little circles have become this loop that got sewed together. Now, the question, so I want d plus delta of this guy to be 0, so that I need somehow, if I do d to these two, to get this. When I do d2, so there's a boundary operator here, so if I do it to this graph, I'm going to get 2 times this graph. So I don't know if you remember, but for ribbon graphs there's a D operator which splits a vertex in all the possible ways. And you will notice that at this 5-valent vertex there's 2 splittings which move this thing away. And then there will be plus 3, there's not 3, but of the following thing. Now, in principle, there's 5 ways to split this vertex. 2 of them produce this guy. 3 of them produce this guy, but 2 of them come with opposite signs. If I explain the signs to you, we'll be staying here till tonight. But 2 of them cancel out, and you get exactly 1 of these.
Okay.
Right? Now,
The point is, it's reducing the valence of the vertex by 1.
it's reducing the
That's what you mean
total. The splitting of the vertex means you find a way to cut. You look at all the ways to cut this into 2 contiguous subsets.
Okay.
And
so
putting
in other
an
insert
edge
one
between.
more. Insert one more edge.
Insert one more edge.
Yeah. Okay.
Exactly.
Yeah.
Now, this maybe had a 1/4, so this will be a 1/2, and this will be 1/4. Now, this 1/2 of this will cancel with this 1/2 of this, if you put the signs correctly. The only question is, where does this get canceled? Turns out that there's no D operator that I can do here because all the vertices are trivalent. But there's the circle operator that I can apply here, which moves this leg to all the possible places around the loop, and there's exactly 6 such ways. So I really need to do D plus TD applied to this and applied to that.
D. What's D? D?
The big D is the circle operator, yeah.
So that's the equivariant differential D plus TD.
Yeah.
Okay. Yeah.
So the little d is the one that splits a vertex. The big D moves the tail to all the possible positions on the circle. Mm-hmm. So this T will cancel this T inverse, and this D will give 6 times this one, which with a 124 will give exactly this 1/4 times this ribbon graph again, and they will cancel out.
So is in the theorem above, was that little d actually equal to little d plus t times big D?
Yeah, it depends if you represent it as MGN unmarked, but I really want to do it as MGN marked, and I take the circle equivariant cohomology. So the little d was what I now call d plus t.
I mean, the point is the circle action is free.
Yeah.
So if you get equivariant cohomology, it's just the cohomology of the coefficient.
But I will actually need this.
I see. Yeah.
So the ribbon graphs are giving you sort of cellular chains. And is the BV operator generally a cellular operator?
It will not work as a cellular operator until you work with these white dots. So there's a much more complicated story which I'm really hiding here. It's not a cellular operator until you find a model where you need to... there is a model which involves ribbon graphs with white and black dots, which I'm hiding here completely, on which the the BV operator can be defined to be cellular. That's a very important point, but Kevin has figured out
that's
how
a
to
different cellular model for MGN.
You need to put MGN with the circle action, so MGN marked, and you need to really do it not for MGN, but for MG with M inputs and N outputs.
Yes.
And you can approximate MG with 0 inputs and N outputs, the one that you really want, by a chain complex whose terms are all the ones for MG AB with A plus B equals to N, and A is greater than 1. Maybe let me explain this afterwards. So far, we've done the calculation of the string vertex, and it would be a computer program which would take more and more time the higher the genus, but the equations that produced that particular string vertex, you could solve them for any genus and any n. It would just become more and more and more complicated computationally, but there is no particular problem to doing that. Okay. Now the second part of my roadmap would be the infinity algebra, and here we have help from Polishchuk. He writes he writes an explicit cyclic infinity algebra for E tau. And here is how he does it. He takes the object O plus L on E tau, where L is a line bundle of degree 1. And he takes A tau to be endomorphisms, or maybe the X algebra of O plus L, but not thought of just as an ordinary algebra, but as an A infinity algebra. And how do you do that? Well, you end up with a quiver which looks kind of like this. Here's O, here's L. From O to L, there's one morphism of degree 0. Right? L has one section. From L to O, there's a morphism of degree 1. From O to O, there's an X1, because H1 of O is one-dimensional, and we call this Xi. And from L to L, there's another morphism of degree 1, and Xi L, also degree 1. And there's two more morphisms which are identity of O and identity of L, which I'm not picturing here. So there's 6. This is a 6-dimensional algebra, a finite-dimensional algebra. Dimensions 3 in degree 0, dimensions 3 in degree 1, homological degree 1. You see the degree 1 elements are Xi, L, and eta. The degree 0 elements are theta, O, and OL. Theta, identity of O, and identity of L. The compositions here are very easy to write. The only non-obvious composition here is that if you do first theta, then you do eta, you get Xi. And if you do eta and then theta, you get Xi L. And the other ones are the compositions with the identities. Everything else is 0. This kind of is obvious. You could give a first-year graduate student the task of calculating this. What Polishchuk does, he tells us higher multiplications. And for example, let me give you an example. M A plus B plus C plus D plus 3 of Xi to the A theta, Xi to the B, Xi L to the B eta, Xi to the C theta, Xi L to the D is some M A B C D. So he writes down an explicit formula for what it means to apply this higher product. Here A, B, C, and D are positive integers. This is the product with so many inputs. And what this means is you put A Xi's in a row, then you put a theta, then you put B Xi L's, then you put an eta, then you put C Xi's, then you put a theta, then you put D Xi L's. This will be this times theta. So this is some coefficient, and the coefficient, this is a modular, but possibly not holomorphic, but maybe, let me just say, quasi-holomorphic form. So I've alluded to in the beginning that there are two worlds when you study Eisenstein modular forms.
This is in the parameters of the elliptic curve.
Yeah, this depends on tau. So, if you've fixed now a particular value of tau in the upper half plane, Polishchuk gives you exactly all the possible non-zero higher multiplications of this infinity algebra, and they all look similar to this.
So somehow this infinity structure is not analytic.
It does not depend. It does not depend holomorphically on tau.
Yeah.
If that's so, it's well defined on H mod the modular group, but it's not depending holomorphically on tau.
There's some analysis that needs to be done.
Well, it depends it's very close to being holomorphically dependent in the sense that these m's, they are polynomials. So maybe this is a good point to discuss this. Maybe let me just very quickly say something about this thing called Kaneka-Zagier theory. Kaneko-Zagier theory.
So is L, do we just take L to be O of T where P is the base point? I mean,
for example. I don't remember what exactly Polishchuk takes.
Somehow math, since this is an
but there was no base point. It didn't matter what the base point of the elliptic curve was. So yes, you take O of the base point. So here's what the story is with these modular forms. This will play a role later on. There's two different types of things if you want to incorporate weight 2 things. So if you're looking at weight 4 and higher, all the Eisenstein modular forms are both modular and holomorphic. That's because when you sum things out, there are some summations, and when you sum, they are absolutely convergent, and there is no problem with the order of summation. But for E2 to define it, you need to pick a particular order, and that screws up modularity. Or holomorphism. Well, it screws up one of them. There are two rings that you can form. One is you can form the ring, maybe let's put Q here. The ring spanned by E2, E4, and E6. And this is, if you look at all the polynomial combinations between these, you get all the things which are holomorphic, and quasi-modular. So being quasi-modular is a concept that you can write down exactly how it transforms under the modular group. It doesn't transform exactly how you expect it. When you act by some transformations, you get some imaginary parts of tau in some results. Now, what Kaneko and Zagier have proved is that there's an isomorphism between this ring and this ring, which are modular quasi-holomorphic forms. So this will be modular forms, but they're not holomorphic, but they're very close to holomorphic. You can fix them by adding some constant times a power of imaginary part of tau. You just need to add an integral power of imaginary part of tau. The statement is that these two rings are isomorphic by the isomorphism which just maps E2 to E2 star. I'm sorry, this E2, maybe I should have put capital E's. Little e's and capital E's are the same thing except for some constant coefficients. So I had my capital E2 before. That was here. This is the same thing, just up to a multiple of some pi's and things like that. Okay? And moreover, there's something very interesting here that's happening. Here I can apply the operator d by d tau. And of course, being holomorphic, applying d by d tau will give another holomorphic thing. But turns out it will preserve this quasi-modularity. On this side, the correct operator is something like d by d tau plus k over tau minus tau bar. So if you apply this modified differential operator, this will preserve modularity and will keep you inside this ring. And the statement is that this isomorphism actually, if you interchange this differential operator with this differential operator, everything gets interchanged. This is an isomorphism of differential rings. But for now, ignore this for a second. What I'm going to tell you, on the other hand, is this. So this guy, this MABCD, is some polynomial with rational coefficients. Sorry, this is true here. This is some polynomial with rational coefficients in these guys. One thing I could do is I could just replace everywhere I see an E2 star by an E2. So I just go by this isomorphism. The theorem that we prove, so here's maybe the first theorem that we prove. So far everything I've said is work of other people.
Before you state it, could you just read what you were, so this operator d by dz corresponded to something that I
Yes,
couldn't
it's
read in
d
a
by
sentence.
d tau plus k over tau minus tau bar.
Tau minus tau bar.
And that k is the modular weight. But the statement is that there is an isomorphism between these two differential rings if you modify your differential operator d by d tau by this very slight modification of it. So the first theorem is applying the Kaneko-Zagier isomorphism to the structure constants of A tau. Produces an A infinity algebra quasi-equivalent to it. So what you should think about is that Polishuk gives us maybe some fairly complicated but elementary polynomial the structure constants of this algebra are polynomials in E2 star, E4, and E6. Replace wherever you see E2 star by E2. Because this is a ring isomorphism to begin with, all the infinity algebra constraints will be preserved. So you get some other A infinity algebra, a priori it could be different. The statement is that this is the same A infinity algebra up to homotopy. And now the resulting things are holomorphic in the variables. So this should solve your problem. I don't remember who it was that asked, but that gives a holomorphic variation of the constants structure. Okay.
Is it? I mean, the actual structure constants of this algebra are model dependent, but can you write down, a Massey product and see that it cannot simultaneously be holomorphic and modular, for example?
I suspect. I don't know. Yeah, I do not know. No. Okay. All right. Now, okay. The next step is we need to find the correct lift to insert. So in the A model, you might remember that we inserted the Poincaré dual class of a point. And you can prove that the correct thing that lives here is 1 over 2 pi I pi over imaginary part of tau dz bar. So let me not go through this derivation. This is a calculation that I actually learned from Nick Sheridan. It's a... I'm sorry that... So the pi's, of course, could cancel, but it's 1 over 2i imaginary part of tau dz bar. It's something that you calculate using some trickery from mirror symmetry. And the difficult thing is why this multiple, and let me not go into that. but you can see that at least this lives in HH minus 1 of A tau. So this is what Polishchuk calls Xi. You might remember that Xi was an element in H1 of O. Elements in H1 of O are 0, 1 forms. So it's a multiple of dz bar. And this is what he calls Xi. So the correct thing here is 1 over 2 pi I Xi. And why am I saying it lives in HH minus 1 of A tau? You should think about Xi as an element in A tau tensor 1. It's a piece of the Hochschild chain complex. And its B, of course, is 0 because there's no multiplication to apply to it. So it gives a cohomology class. And the degree of this cohomology class, you should think about the tensor degree minus 1, which would be 0, plus minus the cohomological degree of this, because I want homological degree, so it lives in HH minus 1 of A tau. Okay? Are there any questions about this?
I mean, is this somehow, are you computing, like the Căldăraru-Spencer map with contracted with the volume form?
Exactly. So you first need to figure out what the correct volume form is. It turns out to be something like 1 over 2 pi I dz or something like that. And then you do exactly the Căldăraru-Spencer class. That's the trick that I learned from Nick. And that tells you the correct multiple here. Any questions? All right. So now the problem is, how do we lift to... So the problem is that Kevin tells you that you should not insert a Hochschild homology class, but a cyclic homology class. And this kind of makes sense. If you remember the formula for the string vertex, there were things with T inverse in them. So those will need to be fed things with T to cancel the T inverse in them. So, all right. So now the question is finding the lift. So, for an elliptic curve, you can explain very concretely what it means to split the Hodge to the Ram spectral sequence, unlike for other varieties. On an elliptic curve, we always have the following short exact sequence. H1 of omega 0, H0 of omega 1 goes to H1 the Ram of E tau, goes to H1 of O. Okay? You always have this very specific short exact sequence, and this is what the Hodge filtration gives you. And you could also understand this, if you want, by saying that holomorphic forms are a subset of smooth forms, and so there's a map from here to here, and you need Hodge theory to prove that the quotient is that. All right. So the particular splitting of the Hodge to the Ram that we care about is we've got our class Xi that we wanted to insert lives in here. We want to pick a particular element in here. Okay? So from the point of view of differential geometry, this is a very clear, straightforward situation. We want to lift this class in H1 of O to the Ram class on E tau. There's a choice. You can put, if you pick any lift, you can put any multiple of dz, would live here. You can put any multiple of dz, and that will change what class you get here, but it will still be a lift. Now, from the differential geometric point of view, mirror symmetry tells you what you want to do. So mirror symmetry tells you want the lift to be invariant under monodromy around the cusp. So the point is that the de Rham cohomology has got Gauss-Manin connection. So you imagine that I've picked not just one lift, I want to pick, so let's say I've picked one lift at some value of tau. Now I imagine that I follow it using parallel transport by the Gauss-Manin connection. You go around the cusp point, the point with the nodal elliptic curve. You come back, and you possibly might come back to your thing plus some multiple of dz. It will still be a lift of psi, but you might come back to something else. The question, what they tell you is that there's a unique lift which is invariant for monodromy around the cusp. Any questions about this?
What's the mirror of this statement? I mean, I'm thinking about the quantum connection and somehow...
Take the point class.
Right.
And you apply the quantum differential equation to it.
Right.
Yes.
You take the derivative and then you take the product with the Kähler class, but the product with the
But
Kähler
that's,
class.
yeah, so that's zero. Okay, yeah.
Zero.
Good.
Okay. So here's a theorem that we prove. The following are equivalent. So the lift is the correct lift. Is maybe let me say an invariant under monodromy. Two, the lift is Gauss-Manin flat. And three, the Kodaira-Spencer class of d tau coupled with this lift is zero. Now, let me explain. So this is because we take a particular value of psi. This is not true. So this is pi over imaginary part of tau times dz bar. So if you choose, so if I choose my value of psi just at one point and I tried to go around, I could always find a locally flat Gauss-Manin thing. But its component in H1 of O might not be this. Mm-hmm. My statement is that if I, so this is if I chose varying size. If I choose this particular one, which is the one predicted by mirror symmetry up to 1 over 2 pi I, the statement is that there exists a lift that's Gauss-Manin flat. The Gauss-Manin flat lift is actually the correct one. It's the one that's invariant under monodromy. And secondly, the Gauss-Manin flatness can be checked by checking that coupling with the Kodaira-Spencer class is zero. This is a consequence of the fact that that the coupling with the Kodaira-Spencer class is an isomorphism between the HH1 to HH minus 1 on an elliptic curve. This is something I also learned from Nick. So what is good about this theorem? The first part was something that you needed to move far away from your elliptic curve. If you sit at one elliptic curve, you cannot figure out what the correct lift is by taking this condition, by just looking around you. You have to go all the way to the cusp and come back. The second condition is something that you can check locally, but it's a nonlinear condition. The Gauss-Manin condition is a nonlinear equation, the flatness. But the third condition is a linear equation, which we can solve purely with linear algebra. So this is the one that we want, because it's linear and local. So now I can explain that now we can do the final computation. So here's what we originally did. This is not how we do it now, but this is the original, more intuitive thing to do. So you fix a value of tau. So when I say fix a value of tau, I literally have a computer program which asks me, give me the complex, the imaginary and the real part of tau. I just have a computer program which will take tau. For this particular value of tau, I compute the MABCDs, the values of these modular forms. There are expressions that you can read from any book you want of these particular modular forms at this particular point tau, and d by d tau of MABCD at this tau. You can calculate. There are formulas in books that tell you how to calculate modular forms. In fact, in Polishchuk's paper, he gives you an expression to calculate. Just sum some power series. These are complex numbers now. They're honest complex numbers that you can calculate. Not symbolically. You really compute them to 12 digits. Approximation. Okay? Then you write some code which produces very big matrices for the following two things. So from 8 tensor 9 plus 8 tensor 7 plus 8 tensor 3, there's the B operator, the Hochschild differential, 8 tensor 8 plus and so on, plus 8 tensor 2. So again, there's formulas for this, which tell you how to calculate the Hochschild differential for this particular part of the chain complex. Turns out, a priori you don't know how far you need to go. You might need to go to 8 tensor 11, 8 tensor 13, but you know that there's some finite level at which you stop. It turns out that 9 is a magic number. And also there is some other matrix for the same thing, for this expression, B11 of nu mu star. You have to read Nick Sheridan's paper for this notation. And that goes to 8 tensor 7 plus and so on, plus 8 tensor 1. So what this means, this is the chain level analog of the Kodaira-Spencer of cupping with the Kodaira-Spencer class of D tau. So this B11 is the operation of contraction, and nu mu star corresponds to the Kodaira-Spencer class. Okay? So you end up with literally some matrices which are 10 million by 1 million, basically. Some absolutely gigantic matrices. This is about size 10 million. 8 tensor 9 has dimension 6 to the 9. And this is 6 to the 8. So just write down these big matrices. I think these blackboards really have a life of their own. And then you want to solve the linear system which writes the following equation. B of alpha equals to 1 tensor psi, and B11 of nu mu star alpha equals to 0. Now let me explain why we want these equations. What they will tell you is the following thing, that if I write now psi plus t alpha plus higher order terms, and I call this psi tilde maybe, then the first equation says that b plus t b of psi tilde is 0 plus higher order terms. So you can immediately see this. B applied to xi is 0. Little b applied to xi is 0. Big B applied to xi, this is cons B differential, is 1 tensor psi. And now little b applied to alpha, or t times alpha, will give you t times 1 tensor psi by this equation. It will cancel exactly that thing. And everything else is higher powers of t. So this equation, this says psi tilde is a lift of psi. The second equation says that coupling with the Căldăraru-Spencer class is 0, which means that it's a correct lift. Okay? So this equation says Căldăraru-Spencer class d tau cup with the psi tilde is 0. So this tells you that you've gotten the correct lift from mirror symmetry. All right. So now you've gotten, the important thing is this alpha. This is what you wanted to find. This is an enormous calculation, but MATLAB is remarkably adept at doing this. Sorry, I will be done in about 5 minutes. So now you've found the correct lift. The final question is, how do you put together everything? So now you need to do some more final computations. So do the following things. Insert psi in this ribbon graph. So this is an operation that's been defined by Kontavich-Soibelman. It's completely explicit. What it says is you want to label this half edge by psi, label all the other half edges in all the possible ways, and read off the outputs from here. So the output here will turn out to be psi t inverse times psi t inverse. Okay? You should think of this, if you want to think in terms of Hochschild homology, it says that if I look at the 3-punctured sphere, and I input the class psi in Hochschild homology -1, and I read off the other 2 punctures as outputs, so the input is from negative cyclic homology, and the output is cyclic homology. So the input is this from positive cyclic homology. I get these two outputs from positive cyclic, from cyclic homology. Okay? Mm-hmm. Next thing you do is you insert psi in this ribbon graph. That was, maybe let me put the 1/2 here, so I get the 1/2 here. So that means, again, I label this thing with psi, and I sum over all the ways to label the other half edges and pair and do all the trickery that Kontavich-Soibelman tell us to do. The output is 0. This is something that you can do by hand if you read Polishchuk's higher multiplications in the infinite algebra. Then finally insert t times alpha in this other ribbon graph. Which had a t inverse here. So that allows me to calculate. So I take the t and the t inverse cancel each other. the alpha evaluates to something in here. And the amazing result of the calculation is that you also get 0. This is, you cannot do without knowing alpha, and you just get alpha. You get 0. All this work is for nothing in some sense. You get 0. Okay? So far there's no sign of the answer. But finally, there's one last calculation that you need to do. Maybe I'll write it here. The final thing you compute is you need to compute the Mukai pairing of alpha and psi, which just means you label one thing here by psi and one thing here by alpha, and this turns out to be exactly the E2 of tau. I wrote computer code which can calculate all of this, and you get a number at the end which you compare, and it's E2 of tau. Now, unfortunately, I haven't had the time, and I'm out of time, to explain why Kevin's formalism tells you not only to just plug in. So up to here, it's kind of obvious what I did. I had my string vertex, and I just took the psi and the T alpha, which was my lift, and stuck them into here. The problem is that that's not enough. You need to do this computation, which comes from some commutator in his Weil algebra. And it's a calculation that I'm happy to show to anybody, but after this lecture. Okay. So the main point is this had a 1/2. This will have a 1/2. So you'll compute 1/2 of this. And there were some normalizations by 2 pi I factors that I have not explained. There were 2 normalizations by 2 pi I. One, we said that I shouldn't be inserting psi, I should be inserting 1 over 2 pi I psi. And one comes from the fact that the correct pairing on the A infinity algebra needs to be scaled by a factor of 1 over 2 pi I. So the end result will be 1 over 2 pi I squared times 1/2 E2 of tau, which is minus 1 over 8 pi squared E2. And you look up what this little E2 that Polishchuk uses is compared to the big E2 that I was using before. And this is exactly minus 1 over 24 big E2. So exactly what we wanted to get. This is the very punchline. You've done the computation. But I have to emphasize that this is strictly a numerical computation. You pick a value of tau, and you calculate the value of this function that Kevin Costello tells you to compute, and you get exactly the number you expected. Now this would be very unsatisfactory, because numerical computations produce numbers, and you never know if they're exactly correct and what's going on. It's a good verification. We now have a completely different technology, which I can't explain, to know that these numbers are true as functions. So this is 0, this is really 0 as a function, this is 1/2 E2 of tau as a function for all values of tau, so that the answer is correct as a mathematical formula. We can prove it with no computer calculations. But this is very special to elliptic curves. If I wanted to do it for something else, I would still need to use a computer. Here we use lots of properties of modular forms and this isomorphism between. We really use the interplay between quasi-modular but not holomorphic, holomorphic, modular but not quasi-holomorphic forms. So I'll stop here. The one part that I'm sorry I didn't explain, I had hoped to explain, I had one more page of explanations, was why this last part, which is a crucial part, that actually gives the term that you want, is the result of the calculation, even though you really needed these things in between. But this comes from Kevin's formalism with Fock spaces for Weil algebras, but I am happy to explain this privately to anybody who's interested. Let me stop here.
Thank you.